Hello and welcome to our discussion of the concept of force and Isaac Newton's laws of motion, Isaac Newton's three laws of motion. So we have to be very concerned with the concept of a force. So force is actually, mathematically speaking and conceptually speaking, it's the product when we multiply mass times an acceleration. So if we look at the laws of motion for Newton, they come in this order. Three laws. The first one is the law of inertia. And inertia says that a body in motion remains in motion, or a body at rest remains at rest unless, except it is acted on by a net external force. So if you push this cart, the cart would supposedly going to go moving forever. If it wasn't for the net external force of air resistance and friction, then this cart will be going on forever. If you are in a car and this car press the brake, they press the brake, what happens is you notice that your body starts moving, is jolted forward. And the reason for that is your body wants to retain the natural initial state of motion, and that is you're moving forward. But it is the net external force in the opposite direction, this deceleration. When you press on the brakes, what happens is you decelerate, which is acceleration in the opposite direction, and that is a net force that causes you to change the initial state of motion to be converted into rest. The second law of Isaac Newton is that force equals mass times the acceleration. And we can play with this law here. So mass, you know that density equals mass over volume. So we can replace mass over volume by density. We can replace mass by putting density times volume, and acceleration we know is velocity divided by time. So in a problem, we can have the question, we have the force and we have the mass, and they ask us for the acceleration, or maybe they give us the velocity and the time and the mass, asking us for the force. So we divide velocity by the time, multiply that by the mass, give us the force. And that is actually how they measure, based on this law, the mass of astronauts in space. You know, the astronaut cannot step on a scale because they're floating in gravity. So in space, and there's no gravity. So what happens is they the way they measure their mass is they push them. There is a device that pushes the astronaut with a known force and a known acceleration. And they have already the value of what is the acceleration by which this device will hit you as an astronaut. Obviously, it's not a very massive or severe force. It's just a reasonable force, and the acceleration is already known. So then when they hit you with that force and with the known acceleration, then they divide the force by the acceleration, and then they will be able to calculate your mass. Are you dehydrated? Have you lost weight? Have you gained weight? So they know the actual, they hit you with an acceleration, and then they measure the force, and then they divide the force by the acceleration by which they hit you as an astronaut, and then that will give them the mass. And they do this repeatedly every week, every 2 weeks, every 3 weeks, every month. to ensure that your weight is within healthy, homeostatic, normal weight. The third law is that for every action, there's a reaction equal in magnitude and opposite in direction. We saw this with the swimming. So the swimmer would push with the feet against the wall, and the wall is going to, in the opposite direction, apply the same force in the opposite direction. And some psychologists believe that this third law of Newton is actually also accurate psychologically. You treat people nicely, they will treat you with the same magnitude in an opposite direction towards you. You treat them well, they treat you well. You treat the people badly, they treat you badly. So that is a standard law. But that does not mean that everybody whom you treat good is going to treat you bad. These are variations, but the general rule is that for every action, there is an equal and opposite reaction. So that shows us here that Newton's laws of motion describe the motion of the dolphin's path. You know, we always know that there is no force without acceleration and mass, and no acceleration without velocity. And obviously, the force is a vector because we accelerate in a direction. Acceleration is a vector quantity, not a scalar quantity, as well as the velocity. That is a vector quantity, not a scalar quantity. That's why you see the force here is pointing to a direction. So an object of mass m is held up by the force of tension. So tension is a force, thrust is a force, weight is a force. They have different names. They're all forces. So the free body diagram always, this is a free body diagram here. This is not a free body diagram. But the free body diagram is always made up of a dot, and the dot represents our system. The system here could be this mass, it could be a car, it could be a spaceship, it could be a cart, it could be anything. We represent it by a dot. And the forces, the external forces acting on this system, this dot, we represent it by arrows. If the arrows are equal, that means the magnitude is equal. If the arrows, one is longer than the other, the one that is longer obviously has more magnitude. Also, the arrows point to the direction of the force. So obviously W points down. That means W is a force that is pulling the mass, pulling our system downward, while T pulls our system upward. So T is the tension and W is the weight. And we said weight is different from mass in that mass is how much matter is in your body, while weight is mass multiplied by gravity. So for a box sliding across a floor, friction acts in the direction opposite to the velocity. So we have forces in all directions. So going horizontally. So this box is obviously moving from left to right. So in our coordinate plane, you have the north, that's y, the east, that's x, and both of these directions are positive. So in our free body diagram, the dot would represent this box. N is north, so obviously the weight is always force pulling us down. So gravity is always minus, pulling our mass down, and the normal force was keeping us from plummeting and pasting to the ground is that it's pointing is that it is it's pointing in the opposite direction of the weight. And we have the net force is pushing us in the right direction, and friction is always written as this subscript, and it is always, friction is a non-conservative force that is always pointing in the opposite direction of our movement. So if we change our movement now from west to east, and we go east to west, friction direction will change. So it would point in the other direction. So friction is always opposing our natural direction of motion. So here we have this system in which there's a wagon on which there is a child. So that's our system. not these two children pushing. These two children are forces. Our system is what we apply the forces to. So this child here is our dot in the free body diagram. So this red dot is going to represent the child on the wagon. On the left, you can have two forces, F1, child 1, F2, child 2. From this free body diagram, you see that F2 is much longer than F1, meaning that the child number 2 is pushing with much more force than the child number 1. Child number 2 is pushing with much force than child number 1. We see that the weight here is the mass of the child and the wagon pushing downward, and the normal force is the opposing force in the opposite direction. So in our free body diagram, we have also the friction is always opposing our direction of motion. So these are the forces that are playing into my system. That's our system. There's the normal force pointing upward. There is the weight pointing downward. There is the friction against the direction of our movement. And we have two forces, the net sum of which these two represent the external forces. So friction is also a form of an external force. So we need to get the sigma or the sum of all the forces. We add up the force of the two children, which are both in the same direction. So we choose the direction of moving forward as plus. So we do plus F1, force of the first child, plus F2, force of the second child, plus minus the friction force, because friction is in the opposite. You see, it's pointing in the opposite direction of movement. So we add all of them, plus F1 for this boy, plus F1 for this girl, and minus F for friction. And that will give us the net force that is being applied on the wagon. Same thing here. We have the same force that as hard as you can push with your max multiplied by an acceleration, applying it on a basketball is going to make the basketball fly far more than the same force on which you exert on a stalled car, for example. So this shows you that the same force exerted on different systems that have different masses are obviously going to produce different accelerations. So here, the air resistance is so low, there is no friction. While here, there is air resistance against the car and friction on the wheels. And here you have to push the much, much heavier car with your body. So that's obviously the car is not going to move as far as a basketball would. The same thing, the concept of the net force is that you are pushing this machine and you are pushing against the ground to move forward, and friction is also fighting against your movement to move forward. So friction is pointing to the other direction while you are walking to this direction, and you are pushing this car, and friction is also opposing the movement of this machine. So when we look at thrust, thrust here is a form of force. So if you look at this system, our system here is our jet. We have our normal force pointing upward, opposing our weight pointing downward. And we have the friction. Don't forget the friction that is opposing our movement in the normal direction. And we have four thrust machines pointing in this direction. When you add up all the vectors, you will see that the thrust magnitude is much more than our friction, that our friction force to overcome this little friction force. So when we look at the swimmer here, you see that the swimmer exerts a net force on the wall. So the swimmer is going to push in this direction, moving to the east direction against the wall. The wall is going to now fight back with Newton's third law with an equal force in magnitude, but is opposite in direction, which makes the swimmer move in this direction. This means that the net external force on her is in the opposite direction. So the opposition, this opposition is the result of Newton's third law of motion, which dictates that the wall exerts a force on the wall, on the swimmer, that is equal in magnitude, but acts in a direction that is opposite to the swimmer force on the wall. So here, when we look at the tension is a form of a force. So your tension is pulling the mass upward. Opposing that tension is the weight of this mass. So the mass multiplied by gravity is pushing downward and your tension is pushing upward. If you're able to lift the mass, that means your tension is more than the weight. That's why the system moves upward. But if the mass plummets and hits the ground, that means the weight far exceeds the tension forced on your rope. So in a perfectly flexible connector, one that is requiring no force to bend it, such as the rope transmits a force known as T, tension. This force must be parallel to the length of the rope. So the uh, the pull that such a flexible connector exerts on the tension. So note that the rope pulls with equal magnitude in force, but in opposite direction to the hand and the mast. So here we neglect the weight of the rope, and this is an example of Newton's third law. So the rope is the medium that transmits. So the rope is a medium that transmits the force in your hand. It's the equal magnitude. So now the rope is transmitting the tension that is on your hand. So when you see here with Tarazan, there's two forces: the force of the weight pulling Tarazan downward, and the tension pulling Tarazan upward. So what's happening here is that if Tarazan is at equilibrium, that means the tension in his hand transmitted to the force in his hands will transmit into the rope, and if the Tarazan is in equilibrium, that means the tension in the rope equals his weight. That's why he didn't fall. If Tarazan, in addition to being in equilibrium, starts to climb up the rope, so definitely that means the force in his arms transferred into the rope as tension is much more than the weight. That's why he's able to pull his body upward. If you are able to do a pull-up at the gym, that means your hands have really strong force and really strong tension that is able to move your body upward. But if you're like me and you jump on that pull-up machine and you want to pull your body upward and then you fall downward, that means the weight on your hands and your arms that is being transferred as tension into the ropes is obviously a lot weaker than your own weight. So obviously either you lose weight or you gain more muscle power in your arms. So here, what are the forces that we are responsible for being able to recognize? There's the force of the teacher pushing this cart forward and the force of her foot pushing against the ground forward. There's also friction that is opposing the movement of the teacher's feet forward and friction opposing the wheels from moving forward. There is another force opposing the walking. So there is the force of walking, pushing and hitting the ground and moving forward. There is an opposing force that is trying to pull the teacher from moving forward. So that is not the same thing as friction. Friction is one thing. This is the force that is equal but is in opposite direction of the teacher trying to move forward. And there's friction that is a natural, non-conservative force that is just making it harder for every motion to move. So if you're moving forward, there is F here. If the car is moving forward, there is another F subscript here. And then there is the force of the teacher pushing the cart, and then there is the opposite in direction and equal in magnitude force that is pushing against the teacher. So these are free body diagram. What does the dot represent? The dot represents this entire system. The teacher, and the cart. And you see that the force is against both. The friction force is against both the cart and the teacher moving. And you see that the floor moving, when you're moving forward, there is the force of the teacher moving forward and pushing the cart forward, and there is the normal force that is opposing the entire system that is being pulled down by the weight, which is the mass of the system times gravity. So this free body diagram here represents to us what are the forces that are interplaying in our system, and our system will only move in the direction of the net force. So if you have four people, one in the north, one in the south, one in the east, one in the west, and they are all have a rope that is connected in like this. Like imagine two ropes connected in the middle like that, and four people, one in the east, one in the north, one in the east, one in the north, one in the west, one in the south, start to pull. Everyone is pulling in their own direction. Everybody is gonna move towards the the strongest force, the one who is pushing with or pulling with stronger force. They are going to be able to move the three ones to their direction because they will represent the net external force. So this is spring. So the spring has this natural length known as x. If you pull the strength far beyond its x limit to this known displacement known as delta x, then if you let go, there will be a restoration. The force will restore backward with a magnitude that is equal to, so you have the displacement, and the displacement here of how much did we displace the string by, and that is going to depend on the coefficient of the spring. What metal is the spring made up of? So that's gonna be important. So we're gonna multiply the coefficient of the spring multiplied by this distance that we have pulled the string back with, and that's going to represent to us with what force will the string recoil and restore.